Welcome back, everybody, to EE240. So just a couple of administrative things before we dive back into the material. So one is obviously the homework is due this Thursday, 5 p.m. sharp. As hopefully you guys saw on Piazza already, the box itself no longer physically exists outside of my office. So we've moved that downstairs. It's, I believe, just in 240 Corey. So make sure you turn things in there rather than trying to put in a box that is not anymore there. And then the other thing is, as many of you guys know, next week is actually ISSCC. And since most of you will probably be there, we won't be having any lectures during that week. There will be a new homework that we'll be putting out. It'll be due basically about 2 weeks from this Thursday. So be on the lookout for that. But again, no lectures next week because I think we'll all be sort of busy going to the conference and hopefully learning about the latest and greatest stuff going on there. So any questions either on logistics or class material so far? Yeah. Okay.
So, first, I'm guessing you mean like total integrated noise as opposed to spot noise? Is that correct?
Yeah, so the question was on question number 4 to basically give the total input referred noise of the current source, or excuse me, of the common source amplifier. I believe this is the one with the PMOS load. Yeah, that's right. So you asked if we were doing integrated noise versus the spot noise. Turns out it's actually not going to matter too much. But yes, if you'd like to treat it as integrated noise, that's fine. Actually, just to make life easier, just do it as spot noise and ignore any sort of capacitance at the output for now. That'll be sort of the most clear answer in terms of what it is that we're looking for. Good. Other questions either on homework or anything else? Sure?
The second question about the same one. When you input refer the noise, it seemed like in the lecture previously you kind of divided by the in-band gain as opposed to the frequency dependent gain. And that was kind of bugging me because the noise is like you're integrating over all frequencies. And like if you applied that noise source to the input, you would get a different power spectrum density at the output.
Okay. So the question was, when we start talking about this input referred noise, there's kind of something that's a little bit annoying in that, at least maybe for spot noise, it's kind of easy because there's a certain transfer function, back and forth. You could always just do the same division. But if you started talking about, for example, input referring the total integrated noise, things indeed get a little bit funky, right? Because you're kind of saying, well, but wait a minute, I'm going through, some net integrated transfer function, and then when I input refer it, I usually just divide by the in-band gain, right, or the DC gain, usually to be more precise. So this is actually a very good question. It's a very common point of confusion. The reason that it's done the way that it's done, meaning that let's say that you indeed had some amplifier that had a transfer function that looked like this, and typically if you were to do the input referred noise from an integrated standpoint, you would indeed basically find the total integrated noise at the output, and then divide it by this DC gain squared, at least in the variance. So that's the common technique that people use, simply because the assumption is that you've made the bandwidth of the amplifier wide enough that basically the signal itself fits within the band of the amplifier. And so the gain you're applying to the signal itself is that DC gain. Now, you're absolutely correct. This is kind of a hand-wavy approximation. So that's why you have to be really careful when you start talking about integrated noise. The only sort of proper thing to really look at is the signal-to-noise ratio after all the integrations have been evaluated. Otherwise, you're somewhat waving your hands. Now, again, with spot noise, it's a little bit easier because everything sort of has the same gains applied to it. But that is indeed a sort of fairly common point of perhaps potential confusion because there is no ideally correct doing it exactly referred back to the input. So that's just usually the approximation that we make. Is that clear? Great. It's a very good question. Other questions on material so far or homework or anything like that? Okay, so if not, let's actually dive back into what we were talking about last time. So I think last time we basically ended up talking about this particular example here where we'd basically been saying that ideally speaking, feedback is not supposed to change the basically SNR or noise characteristics of some amplifier they're using. But then we came up with this example where actually, even though it looked like we were doing quote-unquote ideal feedback, the noise performance actually did change. Now, if you guys remember, the reason we said that this happened was that we weren't really feeding the input directly into the amplifier itself, but rather we were passing it through sort of this resistive network first. Okay? And in particular, we said that what we were really doing was actually attenuating the input signal before we actually fed it into the amplifier itself. And because of that, that's really why the noise actually got worse. Now, Turns out there's actually another way of sort of thinking about this, which generally speaking is potentially useful, particularly if you're interested in sort of spot noise performance, that is an important thing for us to just briefly mention. So one way to sort of make that hopefully more obvious is if I just sort of drew, a box around this piece of the circuit, in other words, just the amplifier with resistive feedback around it. What kind of sort of input signal, what's the units of the input signal you typically think of to feed into this kind of amplifier in this particular configuration? Yeah, you typically feed a current into it, right? Because you'd sort of say this is a transimpedance amplifier. And so you're typically feeding a current into it. It has a resistive input impedance and creating a voltage at the output. Okay? Now, the reason I mention this is that if I have something that, the input that you're feeding into it is a current, if you were going to then input refer the noise of that thing, what would be the dimensions of the noise you would use? Or the units of the noise? Yeah, you'd be doing things in amps, not in volts. Okay? So, again, the reason I bring this up is that it turns out if you think about a generic amplifier, even though last couple times I sort of just drew input-referred voltage sources, in general, there's no particular reason why the amplifier has to have only input-referred voltage noise. In fact, it could have either the input-referred voltage noise, so let's just call that VIN squared, or, in fact, also input-referred current noise, which let's just call that IIN squared. Okay? And again, in that previous example, we could have even taken an amplifier that would have had quote-unquote voltage noise and changed it into something that would have been current noise just by tying sort of that transimpedance feedback around it. Okay? So I don't want to spend a ton of time on this because it turns out that at least in most of the problems we'll work with 240, this isn't going to make sort of a big practical difference as long as you do the calculations sort of the right way, so to speak. But again, if you really have a generic amplifier that you yourself are not designing, you have to be very careful to keep track of not just what the input voltage noise is, but also perhaps what the input current noise is. Okay? And the reason for that is very simple. You can imagine that if I really have an amplifier like this, then depending upon how I drive this thing, for example, if I drive it with a voltage source with a certain output impedance, and then if I change that output impedance, you will actually change the input-referred noise behavior of that amplifier. Okay? Because just as a very simple example, if I was to drive this thing with a voltage source with essentially zero output impedance, then out of the voltage, the input-referred voltage noise from the amplifier versus the input-referred current noise from the amplifier, which one of them will actually affect the amplifier's output, and which one will not? And again, I've driven it now with a voltage source with zero output impedance. Yeah, you'd only care about the input voltage, right? Because the current over here would just see zero impedance from the source and would flow right into the source, right? So it would have no effect on the output of the amplifier. Similarly, as you can probably imagine, if I drove this thing with a current source rather than with a voltage source, now it's only the current noise that's going to matter because the voltage noise, again, is essentially just being eaten up by the current source. Okay? So the real point here is that if you have a generic amplifier like this, it turns out there's an optimum source impedance to use. Okay? And by optimum, I mean source impedance that actually gives you the lowest possible noise. Okay? Now, things actually get a little bit complicated here. Turns out you can probably guess that if I really just had a broadband white voltage noise and a broadband white current noise, and they're totally independent of each other, you could very quickly figure out what the optimum impedance is. It would just be the ratio of the voltage to the current. But more generally speaking, that current noise and the voltage noise might actually be correlated with each other. Okay? And they might even be correlated in a frequency-dependent way. Okay? So when you start getting into that, again, it's not actually too complicated. You can figure out pretty quickly what the optimum source impedance is. But I'm not going to spend a lot of time on it here in 240 because, again, that tends to be more useful if you're really looking at very narrow band kind of things. And when you're really tuning an amplifier just for sort of that spot noise versus the overall integrated noise, there, most of the techniques we've already talked about will tend to be a little bit more useful and straightforward to apply. But if you're interested, this is a topic that you'll see a lot more in either 142 or 242, because again, this is a very important issue in terms of really getting the noise performance at a particular spot frequency to be as good as you can possibly make it. Does this kind of make sense to people, at least from a high-level standpoint? Okay, great. So let's go back to sort of talking about how we're largely speaking going to be doing things here in 240. Now, as I mentioned before, ideally speaking, feedback should not be changing your noise performance. But unfortunately, anytime you put in a real feedback element, particularly if you're putting in resistors, they themselves will also contribute noise to the output. Okay? So it turns out you can, of course, just do the brute force sort of calculation. I trust you guys can all do that, but it is a bit of a pain in the butt. Okay? So typically speaking, people like to come up with sort of simple and fast approximation methods to figure out what the sort of effect from a noise standpoint of each of these feedback elements would be, so that they really don't have to do, the sort of brute force, painful calculation. So it turns out the sort of simplest way to do that is to basically consider the so-called loading of the feedback element onto the input. Okay? And then once you know that so-called loading, you just add the noise source associated with that loading onto the input. Okay, so to make this hopefully more clear, it's probably useful to just go through a specific example. And indeed, let's go through this shunt feedback example that we mentioned a second ago, where I just tie a resistor around my amplifier. By the way, this box here is just my sort of 2-port model of the amplifier. Okay? So the idea is that if I've added this resistor, and I look at sort of its effect on the input, well, because I've put this thing into sort of a shunt feedback configuration, again, my input is essentially going to be in the current domain. Right? So if it's in the current domain, what I'm largely interested in is how much current does this feedback resistor basically drive directly onto that input. And as usual, we could just model that as being 4 kT delta F divided by that feedback resistance. Okay? So just as another example to hopefully make this very clear, let's now do sort of the series shunt feedback, or sort of the voltage gain configuration, where you have obviously positive gain, which, again, we had looked at earlier on. So here now, if we sort of look at the equivalent loading onto the input, here we're sort of actually driving this now in the voltage domain. Right? And just to be totally clear, there's a plus here, a minus there. Right? We're not really modifying the units of the input. That's still in voltage. So what we're really doing is just feeding back through this noisy voltage divider. Okay? Well, if you think about sort of the loading from a voltage standpoint looking back from that terminal, what you essentially have is this RE in parallel with that RF. Right? That's kind of the equivalent source impedance of that divider there. Okay? So just like before, we would say that at least approximately speaking, the voltage noise due to that feedback network would just be 4 kT RF in parallel with RE times delta F. Does this make sense to everybody? Again, key point here is not that this is going to give you precise, exact results. It's just a quick and sort of dirty approximation method that usually will give you pretty close to the right answer, especially if you're interested in just sort of the spot noise density effects of each of these feedback networks. Now, as we'll see a little bit later, in fact, we'll probably start seeing it now. Notice that every time I sort of added these resistors, they add noise into our circuit. Okay? But generally speaking, feedback, like as I said before, we don't really want that to be adding any noise, right? That should just be essentially, question. This is the input referred noise of the original amplifier. So this is like the input referred voltage noise of the amplifier. This is the input referred current noise of the amplifier. Exactly. Well, the box is exactly considered ideal, except that these input referred sources are due to the box itself. But in this model, the box is ideal. Good question. Other questions on this? Or? Okay, so as I was starting to say, we've added all this resistive feedback in, and although it's certainly playing an important role, which is doing the feedback, of course, those resistors are adding noise, and in fact, you could even argue are adding power into our circuit. Okay, and that's kind of bad, right? In particular, if you kind of look at this, let's say I wanted to minimize the voltage noise due to these resistors, right? That would basically mean that I have to use very small feedback resistors. What's bad about that? Why is that sort of really annoying? Yeah, there's going to be a lot of current flowing through them, right? And if you just think of us as like a simple, MOS-based amplifier, that also means you're going to be loading the output of that amplifier very heavily, meaning it's going to be driving a lower output resistance than you may have wanted it to be. Okay? So again, that's bad news. So what I'm going to do now is actually start showing you a little bit as to one way we can get around this, which is actually, rather than using resistors for the feedback, we're actually going to use capacitors for the feedback. So we're going to spend a lot more time talking about this probably in about a lecture or so. But for now, I just want to sort of show you an example topology that would use this, and also walk through a complete calculation of the noise of that, just so, again, you guys have another sort of representative or another example of really doing these complete noise calculations. Okay? So the example I want to do here is basically going to be still our very simple and good old common source NMOS amplifier. Okay? But this time what I'm going to do is I'm going to put it into feedback using a capacitive network. Okay, so this is going to be my input there. I'm going to have a capacitor at the input, which I'm going to call CS. I'm going to have this feedback capacitor, which I'm going to call CF. I'm going to have a load capacitance, which I'm going to call CL. Okay? And again, I'm just going to have some bias current here. All right? Now, before I do anything else, what would the closed loop gain of this amplifier be, assuming I have, infinite DC gain from the transistor itself? What's the ideal closed loop gain in this configuration? At least at DC. Ah, okay. You said it was CS over CF. Why is that? That's correct, by the way, but why is that? Yeah, exactly. So remember, if you had just a normal, op-amp circuit, that, if we go back, that's going to probably die. Okay, we'll come back to that. I'll just have to restart this guy, but we'll come back to it. But yeah, so just while I'm restarting this, if you had essentially a normal op-amp circuit with resistive feedback, right, you would have said that basically the gain is just RF over RS, right? But now notice these are capacitors and not actually resistors. And so because of that, the impedance is 1 over the impedance, impedance is basically proportional to 1 over C. And so therefore, you're going to end up with the inverted ratio rather than the original ratio. And there we go. I'm just getting this back. Okay. And let me just rotate this a couple times. Okay, there we go. Sorry about that. Okay, so I'll just quickly redraw this. Hopefully you guys all already have this. So we've got the CF there. We've got the CS there. We have our input source, VI, and we're going to have some load currents or load capacitance right there. Okay, so as we said, the closed loop voltage gain indeed should be CS over CF. Okay. So now let's start thinking about how we're actually going to get the noise performance of this particular amplifier. Okay? So as usual, what's the first step? Yeah, small signal model. Okay, so let's go ahead and draw that. So as usual, I'm going to have some GM from the amplifier. Let me call that GM-VG. There's, of course, going to be some capacitance at the output, CL. Okay? And then to model the feedback network, I'm just going to, again, draw those two capacitors over here. There's going to be a CF there and a CS here. And then this is going to be VG. Okay, I obviously tweaked, what was horizontal and what was vertical a little bit, but trust me, this is indeed an exactly identical small signal circuit. Okay? So, of course, now the next thing I have to do is add in the noise current due to that GM device. Okay? So before I start doing sort of KCL, KVL, things like that, I claim there's actually a very easy way to analyze this particular circuit. Okay? And to do that, I just want to ask you guys a sort of fairly simple question. Okay? So if I was to take a transistor and tie it into this diode configuration and look into the output resistance of that, what would it be? Yeah, it's 1 over GM, right? Okay, so now let me ask you a slightly more complicated question, although still I claim very easy. So now what I want to do is, I want to take the same transistor, and I'm still going to tie it in a quote-unquote diode configuration, but instead of directly connecting the output to the input, or rather the drain to the gate, I'm going to connect it through this gain that I'm going to call F. Okay? Where, by the way, F is going to be less than 1. So, now what's the output impedance? One over FGM. Okay, there we go. How'd you get that? That's absolutely correct, but how'd you get it? What's the intuition behind that? Okay, yeah. So all you basically said was that, hey, look, the reason that this first thing gave you a 1 over GM in the first place was just that if I had a movement on the drain over here, I had GM times that drain voltage of movement of current coming out of it, right? Well, same idea here, right? If I move this drain voltage around, that's going to move the gate voltage by F times that movement, which is going to mean that the current I get out of it is going to be F times GM. Okay? So now, in particular, if F is less than 1, that implies that my impedance is going to be higher by that factor of 1 over F. Okay? Now, you guys tell me, why do you think I sort of use this particular trick? How is that going to make it really, really easy for us to calculate the noise of this particular circuit here? Okay, you absolutely know what F is. By the way, what is F in this particular circuit? Yeah, exactly. It's just CF over CF plus CS. Okay? Why else? Well, okay, so we do know F, but why else is this very useful? How can we sort of transform the small signal model into something that even you guys have done 3 or 4 times already, and therefore should know the answer very, very quickly? What's the sort of like simplest, noise circuit that we've done like 3 or 4 times already? Okay, resistor. Well, okay, you are right. That's probably the simplest thing, but so I want like the simplest, plus 1, like where I actually have to do an integration to get an answer. Yeah, just a resistor in parallel with a capacitor, right? So if I told you that I had a resistor in parallel with a capacitor, you could again immediately say, okay, I know the integration of that. That's really easy, right? Well, I claim that I can actually transform that circuit up there into some effective resistance, some effective capacitance, and then just some noise current being dumped into it. Okay? Because hopefully this should be clear by now, right? This effective resistance, guess what? That's just 1 over F times GM, right? Because that's exactly what we have in this circuit, right? We just have this diode-connected device. It's not really exactly diode-connected. It's connected through this feedback factor, which I'm going to call F. Okay? Similarly, what's the effective capacitance? So actually, I'll just write this out to be sure it's clear. So R effective is just 1 over F times GM. Okay? What's the C effective? What's that equal to? Okay, yeah, so it's just load capacitance, right? That one clearly shows up directly at the output. And then what we have to do is we're putting that in parallel with sort of this series combination of those feedback caps, right? And just because, again, everything gets flipped over with caps versus resistors, that's going to be CL, and I'm going to abuse notation slightly here, but I'm basically going to say that that's CL plus CF in parallel with CS, okay? Where that just means CF times CS over CF plus CS, okay? So just to maybe, abuse notation slightly less, just to make the expressions a little bit easier, I'm then going to say that that's just equal to CL plus F times CS. Okay, right? Just all I did was a little bit of arithmetic there. Okay? Does this make sense to everybody? Or? Okay, so again, I claim that now that I've done this, life is really easy. So I'm just going to go to the next page to actually complete the calculation now. So as we said before, now our sort of new equivalent model is just the following. We have our noisy current, which, as a reminder, was due to the GM. We have our R effective here, and we have our C effective. Okay? So, okay, just, to make sure everyone's still awake, what is the noisy current due to the GM? Yeah, it's just 4 kT gamma GM. Okay? So what's our output impedance as a function of frequency in the Laplace domain? And you can just use R effective and C effective. Yeah, it's just R effective over 1 plus S R effective C effective. Okay, so just as a reminder, if we were to integrate that output impedance versus frequency, right, that's just going to turn out to be, and remember, to get things in my standard form, you usually pull the numerator out in front, and then you know the integration for the denominator. That's just going to be R effective squared over 4 R effective C effective, which of course is just equal to R effective over 4 C effective. Okay? All right, well, once I've done that, then I claim actually life is really easy. Because of course I can just plug in, as we said before, R effective is equal to 1 over F times GM. Okay? So if I just start plugging everything in, I do IN from the GM times that integrated impedance. And I'm going to be lazy, I'm not going to write that whole expression out. All right, that's just going to be 4 kT gamma GM times 1 over F GM divided by CL plus S F times CS. Okay? Does this make sense to everybody? Or? Okay, now of course, nicely enough, the GMs are going to cancel each other out. The 4s, oh, I'm sorry, I missed a 4 on the bottom down there. Times 4, the 4s are going to cancel each other out. So of course, you're just going to end up with the total noise at the output is just equal to KT times CL plus F times CS times gamma over F. Okay? Oh, I'm sorry. I just, there we go. F times CS. Yeah. Okay, so if I was to compare this result against just a normal common source amplifier, open loop, driving some total load capacitance, what's changed? How has this total integrated noise changed? By the way, what is the total integrated noise for an amplifier, a common source amplifier, open loop, driving some capacitive load? Okay, so yeah, so we said that before, if we had some open loop amplifier like this, just driving a capacitor, you would get that the output noise is KT over C, and let's just be explicit, let's call that CL. Is that it? Is there something else in there? Or? Anybody remember there was this one equation that I told you guys, is like going to pop up, 10 times or something like that? Okay, there's certainly a gamma. I would actually, let me be very clear. We had explicitly looked at that example with the load resistance, right? And we said that that ended up being 1 plus gamma AV, right? Okay, so notice that here with this feedback amplifier, right, what's actually happening is, of course, the load capacitance, instead of just being a regular load cap, now we have that feedback part that's adding on some extra capacitance as well. Okay, so that makes sense, although that's probably not too big of a deal. right? Presumably I can size those capacitors so that they don't have too big of an effect. But notice I have this 1 over f here, right? As a reminder, f is always less than 1, right? Because that's just the capacitive divide ratio there, right? So in other words, what I'm actually doing is that I'm multiplying the output noise by essentially that feedback factor there. Okay? In other words, I'm increasing the output noise by 1 over that feedback factor to be totally precise. Okay? Whereas over here with this open loop amplifier, obviously I added an AV in terms of the output noise, right? But obviously when I refer that back to the input, you'd be dividing by that AV squared, right? So in other words, you are actually indeed paying some penalty from the feedback here. Now, by the way, that penalty is exactly the same as what happened back over here in this example. Because, again, notice that even though we flipped these to be capacitors instead of resistors, what we were actually doing was attenuating the signal before we actually fed it into the amplifier. Okay? Does this make sense to everybody? Or? Yes?
Sorry, are you saying that when you just have the common amplifier, it seems like you're also paying attention to the low cost?
Oh, that's absolutely correct. But notice the gain I would have applied to the signal would have been AV. Right? So if I input refer this is going to become something like KT over CL times 1 over AV squared plus gamma over AV. Right? Whereas here, what is, by the way, my gain? What did we say the gain was? And I'll give you a... Exactly. So just like we had gone through... Just like we had gone through the example with that, resistively, with a resistive feedback amplifier, notice the gain you apply to the signal is different than the gain you apply to the noise. Right? Because the signal is CS over CF, and the noise is by that 1 over F factor. And that 1 over F factor is always going to be higher. Okay? Does this make sense? Or? Okay. Any other questions on this, or are we ready to move on? By the way, we'll still be talking a lot about noise, but this is the final thing that's explicitly just about noise. So any last questions on that? Or? Okay, so if there's no more questions on this, let's go ahead and move on to the next set of lecture notes, which is lecture number 8. So just to kind of give you an overview of sort of where we're going now, we obviously spent quite a bit of time sort of talking about the devices and sort of models and how we're going to deal with that. That's how we sort of came up with this whole V-star or GM over ID based design methodology. We then spent a bunch of time talking about noise. And so now that we have those two things in hand, I'm going to start coming back and talking about actual circuit things that you're going to want to be able to build. And we're going to start out, for example, with current sources. Now, I'm sure you guys have seen current sources many, many times before. But now that we have these kind of model and noise sort of ideas in our heads, I'm going to actually focus on some things that you may not have seen in the past in terms of the design considerations of these particular circuits. Okay? So again, let's just start out with current sources. Now, before I spend too much time sort of talking about current sources, I just need to give you a little bit of a reminder, which is the only thing that makes a current source a quote-unquote current source is that it has a high output impedance. Okay? Now, when I say high output impedance, that always has to be relative to something, right? So in particular, that means it's relative to the other impedances in your circuit. Okay? So as an example, even if something has an output impedance of, I don't know, let's say 10 ohms, if everything else in your circuit has an output impedance of an ohm or a tenth of an ohm, you could kind of call that a current source. Okay? But so as a reminder, really the number one most important thing with a current source is indeed getting a high output impedance. Now, having said that, there's actually going to be many other parameters that will be important as well. Okay? The first one, which we'll spend a lot of time talking about, is the so-called voltage range, meaning how small of a voltage can you put across that current source, as well as how large of a voltage can you put across that current source before it really stops behaving like a current source, meaning before its output impedance becomes low or too low compared to everything else. Okay? Similar as you can imagine, in fact, as you've hopefully already seen in your homework, anytime you put the current source into your circuit, indeed it very easily could add noise into your circuit. So you may obviously care about reducing the amount of that noise in terms of its impact on your final output. And finally, especially with current sources, you tend to care about the accuracy, meaning if you said that this was a 1 microamp current source, Is this really 1 microamp, or is it, anywhere from 100 nanoamps to 10 microamps? Okay. So we'll be talking about a few sort of very common techniques. Cascoding is an example, which I'm sure you guys have all seen many, many times before. And we'll also be talking about actually some more aggressive techniques to really get very, very high output impedance current sources. For example, the so-called gain boosting type of idea. But before we do that, let's just sort of start out with, let's say, the simple, basic, and perhaps even somewhat stupid thing to point out really what is stupid about it so that we can start doing, better current source designs. So the very first time you might sort of be asked to build a current source, at least, with MOS transistors and sort of on-chip elements, you might do something like the following. Okay, so you might just say, well, okay, I've got a power supply VDD. I can always take that power supply, do some, resistive divider off of that supply, use that to set a gate voltage for a transistor, and then just say, okay, well, as long as that transistor isn't sat, I've got a current source, right? Okay, so as I said, this is kind of a stupid thing to perhaps do, but what's bad about this? Why is this a really not so great current source? Yeah, basically you have no idea what the actual output current will be. In other words, this thing is going to vary all over the place. Now, why is it going to vary all over the place? There's a long laundry list of problems, but let's pick off a few of them. Noise in the resistors. What do you mean by noise in the resistors? Okay, so you said the resistors vary with temperature. That is true, but this is one thing that maybe I actually did okay in this particular circuit, right? So as long as I built these two resistors and kind of out of similar devices, and I did all the unit element matching tricks and things like that, at least I could claim that the resistive divide ratio is probably okay, because that only depends upon the ratio of those two resistors.
I guess it depends how you're actually loading this current source, but the load is going to have an impact on what the current source is.
Okay, it is true that depending upon what actual resistance or what actual voltage you place onto that drain, that will change the current flowing through that current source. But actually, that's going to be true for almost all of the current sources. That's kind of like saying there's an output impedance to the current source, and you may not know exactly what the current actually is unless the output impedance is infinite. That's certainly true, but I would claim it's not necessarily particularly bad with this circuit. Yes?
PSRR is really bad.
Okay, so you said the PSRR is really bad. So what you mean by that is that if you change the power supply voltage, the current is immediately going to change, right? And that's absolutely correct, right? Because I haven't done anything particularly magic here. I've just taken some fraction of the supply voltage and used that to set the bias of my transistor there. So indeed, if you change the power supply, current's going to change. What else is really bad about this? Yeah, exactly. So we said the power supply could change. That will change the current. We said that if the threshold changes, well, guess what? That'll also immediately change the current because I just put a fixed VGS on the thing. If the mobility changes, that will change the current. If the Cox changes, that'll, pretty much anything that changes in the transistor will immediately change the current. Okay? There's actually a few other things that are sort of bad about this particular circuit, but we've beaten up on it enough for one day. Indeed, the whole point is, this is bad news. This is not the way you want to do things. Okay? So hopefully, as you've learned many, many times before, if you really want to create a current source, the best way to actually do that is to use what's a so-called current mirror. Now, and I'll just quickly draw it, and then hopefully someone will jump up and sort of be upset with me. So classic current mirror, of course, is just you take some reference current, you feed that into a diode-connected device, and then you feed that diode-connected gate voltage there, essentially to another device to create your output current. Okay, so for example, and typically you'll do a ratio so that you can actually scale the current up or down from that reference current. Now, of course, this is maybe not a little bit, but this is kind of a cheat, right? Because I didn't actually create the current in the first place here. All I did was take that current and copy it, right? So I didn't really exactly solve the original problem of just creating a current from nowhere. Turns out we will talk a lot more about that later on. There are ways you can get reasonably accurate reference currents. But it turns out that 90x% of the time in your analog circuits, creating that current in the first place is usually not so much what you care about. It's more that you care about actually getting enough currents for all of the different blocks in your circuit, or basically creating currents for all the different blocks in your circuit from some known reference value. Okay? So, if you were really doing sort of, let's say, an industry chip that, has to be really sold as a product, and you want, the minimum number of external elements you can possibly come up with, indeed, you would typically have to build some circuit that would create this reference current. But actually, a lot of the times, especially if you're in academia, although even sometimes in industry, it's very convenient to just say, well, you know what? I'm just going to have this bias over here come from somewhere external. Because worst case, if something goes wrong, I can tweak that thing and sort of, move around exactly how my chip is operating and what it's doing and things like that. Okay? So this may sound like a bit of a hack, but trust me, it's not too bad. It's a pretty common thing to do. Okay? So what will typically happen is, let's say, you've built your chip, and it's got a lot of analog stuff on it. What will very commonly happen is, you'll put one pad in some place. You'll have that external current source, sitting out on the board somewhere. And then internally, you'll just feed it into that diode-connected device. Okay? So let's say indeed you went and you did that. And now I'm going to ask myself, or we're going to ask actually you guys the question of, let's say I've got a bunch of amplifiers, all over the chip. And actually, let me draw this the other way just to make the drawing easier. Right, and each of these amplifiers needs some bias current associated with it. And again, I want to slave all these to that known reference current that's external. So again, the sort of simplest thing I might think to do is just go, again, take that reference current, feed it into that diode-connected transistor, and then just feed that gate voltage out to each of these transistors here. Okay? So, anybody see what's potentially very bad about doing things this way? And by the way, I'll give you a hint. This whole chip might be, I don't know, 10 millimeters by 10 millimeters on a side. Okay, and it might be, dissipating something like a few amps of current in the worst case. And I'll see if I can get somebody other than Jethro. Yeah?
Well, there are a couple of things. One, you just built some pretty big antennas.
Oh, okay. So you said I built some pretty big antennas. That is indeed possible. Yeah, no, that is indeed possible. You might indeed pick up some, stuff from, from some RF transmitter somewhere else on the side of the world. That is a problem, although that's probably not the first problem I would worry about. But you said there was a second thing. Okay. So you said that the threshold voltages of this device versus that device might all be different. That's certainly true. That is actually a potentially very big problem, although there's actually another very much related problem. So just since you've been speaking before, I'll try and get somebody else. Go ahead.
With the layout being all over the place, they're definitely not very well matched.
Okay. So you said those devices are not really close to each other. So the devices themselves may not be very well matched. That's kind of like saying the VTs may not be the same. That's absolutely correct. Yeah?
You have really big wire parasitic, so you'll have drop across the wire, which sort of defeats the purpose of having these two.
Okay. So you said you're going to have voltage drops across the wire. Now, I want to be very specific about one thing. Which wire is going to have voltage drops? Yeah?
Well, ideally, there's no current, so there's no voltage drop.
So you said ideally there's no current, so there's no voltage drop. So which wire has no current flowing through it?
Like the big one.
Okay, so this big red one, you said ideally should have no current flowing through it. And indeed, if there's no gate leakage in the transistors, there should be no current flowing through it. Now, this is where I have to remind all you guys that they're called circuits for a reason. So when I drew this little symbol here, that little, 3-wire innocent thing that we like to call ground, what does that actually mean? What do I actually have to draw into this thing to make it a real circuit?
Another wire.
Yeah, there's another wire, right? In fact, there's a pretty darn big wire that connects that guy to that guy, that connects that guy to that guy. In fact, it doesn't just connect those circuits together, it connects all of these circuits together, right? Now, what's the problem with that wire? You said a second ago there shouldn't be any current flowing through that red wire. How about through the ground wire? Is there any current flowing there? Yeah, there's a lot of current, right? Because I just said the whole chip can have amps of current through it. Well, guess what? That wire can have resistance in it, right? And if I've got some current, for example, from some other circuit flowing through here, guess what? You will get a voltage drop between the quote-unquote ground on the two sides of the chip. Okay? Because unless it just so happens that there's the exact same current and the exact same resistance back to the external world from those ground paths, guess what? There will be indeed a voltage drop on the quote-unquote ground potential. Okay? So why is that really bad? Well, notice if this ground is different than that ground, what's going to happen to my VGS on those two transistors? Is it going to be the same, or is it going to change? It's going to change, right? Because remember, all voltages are relative. There's no such thing as one wire that gives you a voltage. There's always 2 points you have to take to create a voltage. Okay? And for transistors in particular, at least for this biasing, it's the VGS you care about, right? So this is really particularly bad because even if this ground here had no current flowing through it, the VGS you created was relative to ground only at this point on the chip, right? If you shipped that same quote-unquote voltage, or really that same one wire, to some other point on the chip, the ground may not be the same, okay? And so because of that, the actual current you get could be very different. So it turns out, don't ever do this. Okay, this is a great way to get fired. Nonetheless, I've seen it actually happen in real chips, but nobody from anywhere here should even dream of doing this. Okay? So the real trick is, if you actually want to do this and do it right, instead of distributing a voltage like that, or really distributing the bias wire to be more precise, what you should really do is essentially distribute the current itself. Okay? So what I mean by that is the following. Let's again take our external reference current. Okay? I'm going to mirror it here just to be able to sort of create additional copies. Okay? So as an example, I'll take that same wire, I'll feed it to a bunch of these NMOS transistors, and then what you should actually route is the current. Okay? These currents are what you'd send out over the entire chip. Okay? Once they get to wherever it is you're trying to send it to, then, and I'll just wrap this around to make my drawing easier, that's when you connect it to a diode-connected device and mirror it. Well, okay, let me draw that a little bit better so that it doesn't look funny. Right, once it finally gets to wherever it's supposed to go, you build the diode-connected device and you mirror it to flow into the circuit you care about. Okay? And again, the big difference here is that now these two transistors and hopefully all of these transistors, everywhere where you do the mirror should be close enough together, and you do a good enough job with sort of the grounds in between them, that you really do believe that the ground or the VDD or really whatever the reference potential is fixed wherever you're doing that mirroring. Okay? So in other words, anytime you have to cover space, you should really route the current. Because again, the current, once you send it into the diode-connected device, the diode-connected device will figure out, well, okay, if I have a certain current flowing into me, then based upon whatever my local supply voltage is, I'll create a gate voltage referenced to that potential. Okay? Does this make sense to everybody, or yeah?
So, and I guess this depends on what your tolerance is and stuff. But if you're going across the chip, is it better to amplify the current and still a large current, or smaller?
Okay. So the question is, if you're going sort of across the chip, is it better to amplify the current and have a large current versus have a small current? The short answer is it probably doesn't matter that much. Because basically in both cases, what you really care about most is essentially how sensitive the receiving transistors are to changes in the potential on that wire. Now, obviously, if you have a very small current, then if you couple any sort of transient signal into it, meaning, or rather really to say it a different way, if the impedance of that wire is very high, and you sort of couple some charge into it, that will translate into a larger relative change at the output. But if you're really going to do things right, you probably don't just route that wire, bare, on top of all of the digital things or all of the noisy things that could possibly be in the world. What you actually do is you basically shield it with metal around it, right? And in fact, you can even build little Faraday cages around the wire where you'd have, the wire in, let's say, metal 2 or metal 3. You'd have a shield of ground or VDD, depending upon what it's referenced to. Let's say the wire itself was in metal 3. You'd put a shield underneath in metal 2. You'd put essentially metal 3 wires with vias both up and down right next to it. And then you'd put a metal 4 on top of it to just create a little cage around the whole thing. Okay? And in case you think this is kind of wacky, trust me, this is done for real. Okay? Because if you do that and you at least connect the grounds appropriately, which you have to be careful of, then indeed you can just shield this whole thing from all of the external junk it might pick up getting routed across the chip like that. Does this make sense to everybody? Or? Okay, so again, keep this one in mind because the sort of quote-unquote current distribution or bias voltage distribution problems, very common problem, so do it the quote-unquote right way. In other words, always route the current, not the voltage. Okay? Okay. So now that we've talked about that, now we can start thinking about sort of another, let's say, new parameter that we've now been exposed to in 240, which is how much noise will these current sources really be adding at their output. Okay? So it should hopefully be pretty clear that if I just took the one transistor, that I had as my current source, and I measured its output noise, that's a pretty easy thing to figure out, right? That's just 4 kT gamma times GM in terms of the noise current, right? But it turns out because we're using these current mirrors, we have to be a little bit careful about things, right? Because typically we're going to have, just as an example, if this device is size, if that device there is size 1, then typically we'll have that other device to be size m, and typically m is greater than 1, right? Typically we multiply that current up, okay? Well, if you think about the sort of equivalent noise model of all this, we now actually have 2 noise sources, right? We have one from the actual output device itself, which again we just said was going to be 4 kT gamma times GM. But we have a second one due to this mirror device here, right? Where much like we had talked about a second ago, this mirror device is connected basically as a diode, right? But you can kind of think of this as, well, if I'm doing the current mirror for sort of my signal current, I'm also going to be mirroring the noise current as well, right? And so if you think about sort of the noise calculation, rather than just getting 4 kT gamma times the GM of the actual output device, now I'm going to get also the GM of this mirror device times that m factor squared, right? Because again, we're working in variances here, not in standard deviations, okay? So if you then actually just remember that the ratio of the GM between these devices, right, GM2 is just going to be 1 over m times smaller than GM1, right? Then you could just pull out the GM1 to the front here, and you see that there's this 1 plus m factor in front of what I would have expected to get from my noise current, okay? And in particular, if I, let's say, had a 1 to 10 mirror ratio, that would mean that my noise current is 10 times larger than I would have thought it was. In fact, actually 11 times larger than I would have thought it was, just due to the noise current of this one device here. Okay? That's kind of bad news, right? That basically says that if I really want to mirror things up like this, then I could be picking up a lot of extra noise if I'm not careful about it. Now, the good news is there is something, actually there's a couple of things you can do to fix this, both of which are actually sort of hinted at on the slide here. So what's the first, let's say, really brute force way of trying to make sure that you don't pick up too much extra noise by doing that current mirroring? Yeah, just make m small, right? So if I make m small, then whatever this multiplying factor is will just be a smaller factor. Now, why do I tend not to want to do that? What's the obvious penalty? Yes, which is written on the slide. Yeah, you have to spend power for it, right? Because obviously, if I said that this thing over here has to be a milliamp, let's say I make m 1, well, now I'm spending 1 milliamp over here. Why am I upset about spending 1 milliamp on that left-hand branch over there? Yeah, well, because to put it another way, you said it's a lot of power to spend needlessly. I'm getting absolutely zero functionality out of that thing on the left, other than just making sure my stupid circuit is biased, right? So that's typically not what you want to be spending your power on, okay? So good news is there's another way of at least mitigating this problem. And it turns out that that particular solution is probably something you wanted to do anyways. So what else could you do to actually get rid of this particular issue? Or at least help this issue? RC filter. Okay, you said something about an RC filter. I'm going to make it even easier than that. I'm just going to add a capacitor somewhere. So where should I put that capacitor? Yeah, at the gate, right? So if I really do this right, what I should do is put a big fat capacitor between that gate voltage and ground there. Okay? So in terms of noise, the reason this helps is if I really make this big enough, what I'm going to do is I'm going to filter the current noise from that mirror stage so that it doesn't cause a very big voltage variation at the gate of the next transistor there, right? Or to say it another way, I'm going to make it so that the noise bandwidth from this mirror device is way, way smaller than the noise bandwidth actually at the output transistor. Okay? Now, as I mentioned a second ago, this is actually a very good idea anyways, because as we were discussing a second ago, what you really want is, at the end of the day, when you created this voltage here, you want the impedance of that voltage source to be as low as possible, right? Because it's supposed to be now a voltage source. So if it's indeed supposed to be a voltage, putting a big, huge cap on it to make sure at least the high frequency impedance is low is actually a really good idea, right? It'll make sure that even if there's some transient movement on ground relative to, let's say, the rest of the world, that'll keep that gate voltage very well coupled to its own reference potential. Okay? Does this make sense to everybody? Or? Okay, so now let's say indeed that I went ahead and I did that. I added this capacitor in, okay, so that I can assume that this M factor gets filtered out, meaning I'm really just left with 4 kT gamma GM as the net remaining noise current. Okay? The question I want to now ask is the following. So, as we know, if I just had a resistor, right, and let's call it Rn, that resistor would have had a noise current density of just 4 kT over Rn. Okay? So what I want to do now is I want to define sort of like an effective noise resistance for this current source. Okay? And as it hopefully should be obvious, the effective noise resistance of this, CMOS or transistor-based current source is basically just 1 over, there we go, 1 over, and I don't know why I wrote it this way, but basically that's just 1 over gamma times GM. Right? Does this make sense to everybody? Or? Okay, so why do I point this out? Well, so for here, remember, I'm going to assume that I put a big, huge capacitor there, so that I essentially got rid of that M factor. If I didn't have the cap, the M factor would still be there, but let's assume that I at least did that right. Okay? So, if my noise resistance is 1 over gamma GM, there's an important point to notice here, right? The whole point of me putting this current source in was that I wanted a high output impedance, right? In particular, I wanted to get the RO of the transistor as my output impedance, right? But notice, from a noise standpoint, I'm not getting 1 over RO. I'm actually getting 1 over GM. Okay? So in other words, I'm getting a lot more noise current than I would have if I literally just had a resistance of RO there. Okay, and in particular, I just rewrote this slightly right here. If, I was expecting an RO, I have AV0 of a lower noise resistance. Okay, and remember, for noise, at least in the current domain, lower resistance is higher noise. Okay? So that's kind of the point that's really being made here, is that if you pay close attention to what this active current source is doing, I'm only boosting the output resistance from a sort of signal standpoint. But in terms of the noise, I actually have a much lower noise resistance. Okay? So the natural question that this may bring you to ask yourself is, well, okay, hang on. So what we just said a second ago is that if I took a transistor, right, and I measured, and I said, okay, this has a certain RO of output impedance, and I measured the noise flowing through that transistor, and I compared it, for example, with just a resistor whose value was equal to that output impedance, we just said that this transistor would have more noise. Okay? So the natural question to ask ourselves is, why in the world did we use the transistor in the first place? Why wouldn't you just use a resistor for the current source and get a lower noise out of it? Does anybody know?
Well, the resistor will only give you the right current for 1 voltage.
Okay, you said the resistor will only give you the right current for 1 voltage. It's very much related to that, but let's dig in that a little bit more. So you're right, it'll only give you the right current for 1 voltage, although I could argue that technically the transistor will only do that too, because it also has a finite output impedance.
Okay, but the sensitivity is more.
So you said the sensitivity of this is more.
Current will change. Well, maybe.
Yeah, no, maybe not, right? Because like I said, I've made this resistance the same as the output resistance of the transistor, right? So at least at a particular bias point, the sensitivity is the same. But what are you paying for it? Yeah.
We want really higher current
Ah, okay. So you've hit it now. So what you basically said was that the big difference is how much voltage you needed in the first place to get the nominal current. Okay? And so let's just draw a simple picture that hopefully will make that clear. So let's say I do just a drain current versus drain voltage plot for both the transistor and for the resistor itself. Okay? So for the transistor, we should have something that, let's say, looks like this, right? And by the way, I drew a kind of crappy transistor that doesn't have great RO, but it's fine. It'll make the point just fine. Okay? So when we take the transistor and we use it as a current source, what we're basically saying is that we're getting the sort of output resistance that's the slope of the curve right there, right? Let's say we indeed wanted to take a resistor that would have the exact same output resistance and use that to bias our circuit instead. Okay? Well, what I would then have to do is take that same slope, but start it from 0 voltage, right? Because it's a linear resistor. You have 0 volts. You get, well, okay, that's true for everything, but the slope is always that same slope, right? So in other words, we always have that resistance in terms of the slope between the voltage and the current. Okay? So now if you'll notice, and maybe I'll do this in a slightly different color so it's easier to see. Right? If, let's say, I wanted this amount of current here, right? I'm sorry, actually, this amount of current. Then for the transistor, this is how much voltage you would need to get it, right? Whereas notice, if I use the resistor, obviously I need much, much higher voltage to get the same current. Okay? So that's really the biggest difference. The difference is that if you use a transistor, you'll be able to get that same current for a much lower nominal voltage drop across it. Whereas for the resistor, to get that same current flowing through it, and to get, of course, the same output impedance, you're going to need a much bigger DC voltage drop. Okay? Is this clear to everybody? Or? All right, now, why does that matter? Why is it that oftentimes I will use the transistor current source because of this? In other words, why is it that having lower voltage drop across the current source is actually a very important thing, even from a noise standpoint? Okay, yeah, you said you're only working with like 1 volt. Or to say it another way, remember the maximum swing you can get at the output of your circuit is typically going to be tied to how close to 0 you can make this drop across the current source, right? So in other words, as we'd mentioned a couple lectures back, if you could maximize the voltage swing, then even for the same number of millivolts of noise, you might actually have a better signal-to-noise ratio. Okay? So in fact, it may indeed be the case that even though pushing this, pushing the voltage, the minimum voltage down like this, caused you to have extra noise from the current source, if it brought you back more in terms of the swing you can get, from a net SNR standpoint, that might actually be a much better thing to do. Okay? Does this make sense to everybody? Or? Okay, so keep this in mind, because actually this is going to be kind of a recurring theme. Okay? Because as you noticed, hopefully, a second ago, there's kind of this trade-off between, well, if I wanted a small minimum voltage, meaning a small sort of minimum voltage drop across the current source before it craps out, then I had to pay for it from a noise standpoint, right? I got this GM times RO larger noise than I would have had just from using the resistor. Well, so the recurring theme there is it turns out that overall there's always going to be a trade-off between essentially that minimum voltage you can use across a current source and how much noise that current source is going to be adding. Okay? So let's look at this for the simple example of the MOS transistor. Now, to do that, I'm just going to define sort of one parameter that's going to be a little bit of a hack, but bear with me, it's not so bad. Okay? So if we had a sort of simple long channel device where, with some bias voltage there, and we asked ourselves, what was the sort of voltage you needed across it to make sure the device was in saturation, meaning to make sure that you had a sufficiently high output impedance? Well, for the classic sort of long channel device, that VD sat would have just been V star, right? Now, remember, we're dealing with short channel devices, so V star doesn't really correspond to the saturation voltage. But to kind of fix that, in somewhat of a hack way, but it'll work, we're now just going to define some new sort of basically parameter that I'm going to call this Vmin. Okay? I'm going to say this Vmin is, again, kind of the minimum voltage I need across the transistor to make sure it has a sufficiently high output impedance. And just kind of by analogy, I can always say that that Vmin is just some arbitrary k times V star, right? So again, if I had a long channel device, this k would just be equal to 1, right? Because the VDSat or the Vmin would just be equal to V star. For a short channel device, it may not be necessarily 1. It could be somewhere between 1 and 2. But nonetheless, there's going to be a proportionality between the V star that you use and the actual minimum voltage that you use. Okay? Well, the reason I bring this up is that if you notice that I say here, okay, well, my noise resistance, as we said before, was just 1 over gamma times GM. Again, don't worry about this 1 plus M factor. That's really just coming about from the current mirror. I can rewrite that GM, basically, again, just by definition, as being 2ID over V star, right? And then if I just use the definition up above, which I can sort of flip around to say that V star is equal to Vmin over K, then if you just substitute those two things, you can quickly see that basically the noise resistance is actually proportional to that Vmin. Okay? So in other words, the larger the Vmin you allow, the higher the noise resistance, or equivalently, the lower the noise current you can actually get. Okay? So again, this is really telling you that there's this direct trade-off between essentially how much voltage can you put across the current source versus how little noise will that current source add into your circuit. And in general, there may indeed be some optimization that you could do where you'd actually find what the best overall signal-to-noise ratio you can get is based upon trading off essentially the swing at the output of your circuit versus the noise being added by your current sources. Okay? Does this make sense to everybody? Or? So, just to be sure that this is, let's say 100% clear, I just want to show one more example. Okay? So you'll notice here that I now switched from CMOS to bipolars, not because we're really going to be doing anything with bipolars here in the class, but just to, again, make sure that this concept is pretty clear. So if you'll notice in the circuit on the right over here, rather than just doing sort of an exact bipolar version of the CMOS current mirror, I added in these degeneration resistors. Okay, and again, just to be 100% clear, the sort of contrast is the following. Right, I could have done instead something that would have just looked like this. Right, I would have just directly grounded the mirror device and also directly grounded the output current source. Right, this would have been sort of the contrast. So, I claim that in bipolars in particular, you really want to use this version of the circuit. In other words, you really want to add that degeneration resistor in. Why is that? Why is it really important to add that degeneration resistor in, particularly in a bipolar current source? Yeah?
You degenerate the GM so less current noise shows up at the output?
Okay, so you said I degenerate the GM so that less current noise shows up at the output. That's absolutely correct. Why is that particularly important in a bipolar circuit versus, for example, in an MOS circuit like this one over here? So you said they usually have a higher GM to begin with. So to be more precise, right, for the same given bias current, a bipolar gives you a much higher GM. So to use our sort of 240 terminology, what is the parameter that's sort of changing there? Yeah, the V star. What is the V star for a bipolar transistor? Okay, it's really close. It turns out it's double of that. Because remember we said its GM is 2ID over V star, so it's actually like 52 or whatever, whatever that number turns out to be. Okay? But remember I kept telling you the magic V star you're typically going to use is something like 200 millivolts. Turns out in a MOSFET, it's pretty darn hard to get, below about 100 millivolts or so of that V star, maybe even about 80 millivolts or so. Bipolar, at least if it's a good device, indeed you're going to get 50, maybe 60 millivolts for that V star. So that says that if you're not sort of, especially if you're talking about this current source kind of application, right? Remember, GM doesn't really buy you anything in a current source, right? In fact, all it does is actually hurt your noise performance, okay? Because your noise resistance or your noise current is GMRO larger than it would have been if you just had the resistance in the first place, okay? So what's happening in this bipolar circuit here, indeed you add this degeneration resistance. just to reduce the GM coming from, or the effective GM coming from those bipolar current sources. Now, I'm not going to walk through the math because it turns out it's not actually particularly important. But what you can see is that even down here at the end, even with this sort of source-degenerated version, there's still a direct trade-off between essentially the minimum voltage you can tolerate across that current source and its effective noise resistance. Okay? Obviously, the exact factors are a little bit different. But actually, it turns out that here, if you really wanted the lowest possible noise, you would indeed maximize that source resistance, or the RE in this particular case. But, hey, for the same current, if you dump that into that source resistance, or that emitter resistance, voltage drop is going to have to go up, right? So just like with a normal resistor, just like with a MOSFET, there's still going to be a direct trade-off between the minimum voltage you can support and the actual noise resistance you get. Okay? Yes?
Just to check, the noise that you get, is it presumably you get from RE kind of get canceled out somehow, or you'll also get some noise from adding that resistor?
Oh, so you were asking the question of, well, hey, wait a minute. When I added this resistor, doesn't that resistor also add some noise? The answer is absolutely yes, it does. But notice, in the absolute limit, if I made this resistor basically infinitely big compared to the GM, or the 1 over GM of that bipolar device, what would happen is the noise of the bipolar device would completely go away, because the GM would be completely source degenerated, right? So what would happen is you'd be left with only the noise from the resistance itself. So in other words, if you actually looked at, if I allowed the voltage drop to increase, then if you actually looked at the noise current as a function of that source resistance, it would indeed monotonically go down. It would not go to, it would go to essentially just 1 over RE in the limit, or in terms of the current proportionality. Does that make sense? Or, okay, great. Okay, so we spent a lot of time sort of talking about noise in these current sources, but now let's start talking about basically techniques we can use to actually boost the output impedance, right? So this hopefully you guys know very well. Oftentimes just using the single sort of device, especially if it's a short channel device, just doesn't quite get you high enough output impedance for you to really be saying, yeah, this is sort of a current source the way I want it to be. Okay? So hopefully if you've seen, again, many, many times before, classic technique to actually boost that output impedance is just add this so-called cascode device on here. Okay? Now, before I sort of ask you guys, exactly what the effect of that is, although I think we talked about that once already in terms of, for example, maybe we'll just write it out now. So, for example, let's say if I just had that one transistor by itself, you would get an RO of output impedance. Whereas, of course, if you do this, you're going to get GMRO times RO of impedance. So, the question I want to ask you guys is, what's the sort of physical mechanism that allows that to happen? Why is it that you're boosting the output impedance in this particular case? What's sort of happening that allows that? Yeah.
The drain current of the cascode device is super linear, so it doesn't change the drain voltage on the lower device as much.
Ah, there we go. Okay, so the second piece of what you said is, I think, really the critical part of it. Okay, so just to make sure that everybody heard and for the camera, the real trick here is that what that cascode device is doing is it's actually trying to fix that Vx right there. Okay, it's trying to reduce the variations on that Vx. Okay? Because here's the whole idea, or here's the whole trick, right? If I take that bottom transistor and I plot its ID versus VD, right? Then hey, there's no magic, it has some, right? Well, in the case on the right, if there's a certain swing in the drain voltage, as an example, let's say plus minus 100 millivolts, right? That's going to translate into a certain swing on the drain current, right? In other words, you're just riding on the slope of that particular device there. Well, with the cascode, which now I'm just going to do in a different color so it's easier to see, let's take the particular example that I gave. So let's say that indeed I was interested in this plus minus 100 millivolts variation on the output over there. How much variation would you see in Vx for that same plus minus 100 millivolts at the output? I don't need a number, by the way, just parametrically. Yeah, exactly. It would be GMRO times smaller swing. Okay? So if the output was plus or minus 100 millivolts, the Vx swing would be plus minus 100 millivolts divided by GMRO. Okay? So keep this in mind, because this is actually going to be useful a little bit later on. You should remember that if you looked at basically any sort of common gate or essentially cascode kind of topology, the swing on the drain is always GMRO times larger than the swing on the source. Okay? Now, and again, to go back to this earlier picture, the reason that's really important is now if we've reduced that swing by GMRO, well, now I'm only applying, for example, this much swing in the drain voltage on that bottom device. And of course, if I have a lower swing in the drain voltage, then equivalently, and I apologize for the sort of bad picture, it's a little bit small maybe, but for a smaller swing on the drain voltage, obviously there'll be a smaller change in the drain current. Okay? Does this make sense to everybody? Or? Yes? Okay. So just to be totally clear, let's actually label things. So let's call that, I think I labeled that M2 and M1 here. So it would be GM2 RO2 times RO1. Okay, so again, this is M1, that's M2. Okay, so it's really the gain of the cascode device that's being applied to knock down the swing on that Vx node right there. Is that clear to everybody? Or? By the way, that's just another way of saying that, again, if you looked at the drain versus the source of a device, the drain swing is always GMRO of that device larger than the source swing. Okay? Is that clear? Or? Okay, so let's actually go and sort of take a look at what this cascode actually buys us. Okay? So what I'm showing you here is a plot of the output resistance of either the cascoded structure or the non-cascoded structure as a function of the actual voltage you apply across essentially the current source. Okay? So again, this is hopefully maybe not too surprising. You kind of have to have a certain minimum voltage before you can actually see that there is a difference between the output impedance of the cascoded structure versus the non-cascoded structure. Okay? In other words, if you're below sort of this certain voltage, there's actually not too much of a difference between those two. Okay? And of course, it's only once you get sort of above that voltage, then the cascode really starts coming into the picture. Okay? Now, hopefully you guys talked a lot about this in 140 already, right? You talked about, well, how do you actually bias this cascode, right? In other words, you want to make sure that, and I'll just draw the picture, you want to make sure, for example, that if you do have that cascode device, say there's a VB2 there and a VB1, right? As an example, if you picked that VB1 too low, you'd squash that bottom device, it would come out of saturation. Again, that would be bad news, right? So in the example I'm showing here, obviously I've biased it so that that particular case does not happen. But nonetheless, it does say that there is sort of a certain minimum voltage across here that you need to maintain to actually get some benefit from the cascode. Turns out there's actually a more sort of general and interesting question to be asked here, and may actually have a somewhat surprising answer relative to what you may have heard in the past. Okay? So the question I'm going to ask is the following. Let's say I indeed have this cascode structure. Okay? Well, of course, there's some bias on these two gates right here. The question I want to ask myself is the following. If I look at that internal node there, how should I choose the bias for that internal node? Of course, relative to, and let me just label that device as M1, this device is M2. The question I'm going to ask is, how should I choose the bias of that intermediate node there relative to the V star of the bottom device? Okay? Because you can imagine if I make that V star sort of lower, I'll have less output resistance from the bottom device, but I have more of a chance of getting the cascode sort of into saturation, right? So again, you can ask yourself as you move that bias around, what sort of gives you the best overall result from an output impedance standpoint? So it turns out the somewhat surprising result is that you actually probably want to choose that bias kind of as high as you can. Okay? And the reason is the following. So if you look at this plot, where again, literally all I did was move this bias point around, obviously by changing both either this bias voltage or by changing the size of that cascode transistor. What you'll notice is that below some certain voltage, they all kind of give you about the same output impedance. Right? They're all kind of comparable. There's not really much of a difference. But notice once I get above some certain voltage, then you really actually start seeing differences between, for example, any cascode at all and the non-cascoded device. But even more than that, and I'll just label these because they might be a little bit hard to see. This is K of 0.5. This is K of 1. This is K of 1.5. What you can actually start to see is that pretty much no matter what voltage I'm at, the output impedance you get from something where you've biased that middle node higher is always higher. Now, at some regions, it's kind of basically the same, but it still says that if there's ever a situation where you actually get that higher bias voltage, the higher output voltage, then the output impedance of the cascode structure with the high middle bias will actually be higher. Okay? So to put this another way, you really do want to choose that higher bias voltage, simply because there's really not much penalty for doing it at any of the lower voltages. And if you just so happen to actually get a larger voltage across the structure, you will indeed actually get a higher output impedance from it. Okay? So again, the sort of perhaps somewhat surprising result, especially if you just think of this from a sort of simple long channel saturation versus not analogy, is that indeed you will tend to want to make sure that you have as much bias across that bottom device as you can, simply because that will actually basically get you the highest possible output impedance pretty much in all of the scenarios that you can think of. Okay? Now, there are some caveats to this when you start thinking about sort of the extra capacitance you're introducing. I'll talk about that more a little bit later on, but do keep this in mind. So, any questions on that? Or? All right, so I'll see you guys all on Thursday.